We can summarize this lesson in just a few sentences. So first of all, a recursive function is equivalent to a loop if it is tail recursive. Second of all, to write function this way, we need to find an accumulator, an argument in which we can build the result incrementally. Third of all, to find the accumulator, we start from an invariant, so a statement that is true about the arguments of the function at each recursive call, and we use the principle of communicating vases to build the result in there, in the accumulator. This approach is called invariant programming, and in fact it's the only reasonable way to program loops. And finally, it's useful in all programming paradigms, not just functional programming. We've introduced it in functional programming because this is our first paradigm. The others will build on top of this, but this technique continues to hold. Now, to finish this lesson, let's tackle a bigger example. So let's use invariant programming to define the function pow(xn) that calculates x to the power n, where n is greater or equal to 0. So we will define three functions that progressively have better properties. So let's start with a naive definition here. X to the 0 is 1. X to the n is x times x to the n minus 1, where n is greater than 0. This gives a first program, pow1, which is incredibly inefficient, both in time and space. In fact, there are two reasons. One reason is that this function is not tail recursive. There is, in fact, another reason, if you have an idea how to calculate powers, is that it does way too many multiplications. So, for example, if I want to calculate x to the 16, pow1 will do 16 multiplications, whereas I can get by with many less. If I start with x to the 1, I square, I get x squared. I square again, then I double the exponent, I get x to the 4th. I square again, the exponent doubles again to x to the 8th, and I square again, and I get x to the 16. So this has 1, 2, 3, only 4 multiplications instead of 16. So, in fact, we can improve this function in two ways. We can make it tail recursive, and we can take advantage of the trick of using the squares. So let's first use the squares. Let's make a better definition of x to the n. Notice I've added a third rule to this definition, and I've added in blue here new conditions to show where this third rule applies. This third rule is exactly going to apply in the square case. So for example, when n is even, then I can say y is x to the n divided by 2, which is going to be an integer, and then the result is y squared. And the second rule then will take over the cases where n is odd, which is not handled by the square rule. So this definition will calculate x to the 16 much more efficiently than the previous one. Notice that both of these definitions are called specifications of the power function. Specifications because they are purely mathematical. They have no program code in any programming language. They give a purely mathematical definition of what we want to calculate. So here is the second program, the one that uses the approach of using the square. So here we have, if n is odd, I do x times x to the n minus 1. And else n is even, I do x to the n divided by 2. And then I return y squared. Y is the x to the n divided by 2. So this definition is better than the first one, a lot better, but it is still not tail recursive. So how do we make it tail recursive? How do we make it so that it's a true loop? In order to do that, we need an invariant. How can we calculate an invariant? Find an invariant in this case. We need an invariant where the result appears in part of it as an accumulator. What can we accumulate? What do you think? In fact, the invariant is not so hard to find. It's quite simple. We're going to use multiplication. X to the n is equal to y to the I times a. Notice here in the left-hand side we have x and n, which are in fact constants during the execution. And y, I, and a are values that can change during the execution. We can have different values as long as the invariant is true. So this distinction between part of it as constant and part of it that will vary is inherent to this invariant approach. So to represent this formula, which has 5 variables, we can represent it compactly with y, I, and a, the 3 that can change. Whereas x to the n, x and n do not change, we don't have to have them in our notation. So this allows us to write it much more compactly. You have y, I, a, initially is x, n1, x to the n times 1. And now we will decrease I while keeping the invariant true. And there's 2 ways to do this. So the way coming from the first mathematical definition is simply the I becomes I minus 1, and then the accumulator has y times a in order to compensate. The other way, using the square, is the I, we have here I divided by 2, and then in order to compensate, we have y times y. So we have y times y to the power I over 2 is the same as y to the I. So we have these 2 rules. And now we can write the program. So we have here an internal loop, pow loop, with 3 arguments, y, I, and a, the 3 arguments that are part of the invariant. If I is equal to 0, then the result is a. Otherwise, if I is even, so now we're going to apply the 2 rules. If it's even, we apply the square rule. So we have y squared, I divided by 2, and a. If it's odd, we have y, I minus 1, and y times a. So this program is a true loop. It is tail recursive, and it uses very few multiplications. So this program, we designed it starting from the mathematical definition and then using invariant programming to turn it into a tail recursive program. Notice how elegant it is. Let me finish this lesson with a look to the future. Notice that changing one part of the invariant forces the rest to change as well, because the invariant must remain true. So the truth of the invariant is what drives the execution, the fact that the invariant must stay true. It's like a motor. Programming a loop means finding a good invariant. So once you find a good invariant, the coding part is easy. So the whole trick is learn to think in terms of invariants. Loops are invariants. Thinking of loops is thinking with invariants. So don't think of loops as calculations that are repeated. Think of loops as formulas that are true, as invariants, and see how you can push them to go in the direction you want. And this leads us to a more general form of invariant programming called goal-oriented programming, a very powerful and general technique. Goal-oriented programming, we have a goal and the program will always work toward that goal. And that is what drives the calculation. So invariant is a particular case of this. We will see another example of goal-oriented programming, a very nice example, when we program with trees in lesson 5.